All right, hello everyone. Welcome to my channel. I do educational videos on this channel, mainly on subjects that are important to me, but I think they would be important to you if you knew about them. Today is the 165th video that we've done on the reciprocal system of theory. And this is a theory that was devised by Dewey B. Larson back in the 20th century, starting from his first inklings into uh, the reciprocal nature of space and time in about 1930, and he kept at it for about 60 years until he died, until 1990. Put out many books, articles, gave a lot of talks. Had a few followers, but not too many, and very, very, very few people know about it. I've actually never met another person who knows about it. And I've known about it for over 20 years. So in 20 years, I've met zero people that has that have known about this. Okay, now the basic idea behind Larson's system is that the ancient Greeks thought the universe was made out of matter, atoms. And then eventually, 2,500 years later, Einstein came along and said, well, no, E equals mc squared. The universe looks like it's made out of matter, but really it's really energy. Energy can be converted into matter and vice versa. And Larson came along a few years later, 25 years later, and said, well, no, the E equals mc squared pretty much shows that the universe is not made out of either matter or energy, because they can be converted one to the other. And so therefore, there must be something that underlies both of them that is more fundamental. And that is the c squared part, motion. The universe is made out of motion. And some other people have come up with that in the past. But what distinguishes Larson is that he defined motion as the relationship between space and time. Now, we do see that relationship clearly in the most basic kind of motion that we know of, which is speed. The car is moving 20 miles per hour. 20 miles of space in 1 hour of time. Space over time, that is speed. But any kind of relationship between space and time, which is always going to be a fraction, is also motion. And Larson says that, to quote a term that David Icke uses, opposames. That space and time are opposames. They are the opposites, but they are also the same, in that they have the same qualities. That is the basic idea behind a generalized reciprocal relationship. And so Larson posited that space, we know space to have its coordinate aspects. It is 3 or more dimensions. Euclidean space, XYZ coordinates. And therefore time also does have those 3 or more coordinates. Coordinate time is what he called it. And then we know about time that it is always progressing. It is always getting later and later and later. That is clock time. But then by the reciprocal relation, there is also a clock space. So that is that things are always getting farther and farther and farther apart. And that was detected by the Hubble telescope way back in the 1920s, observing that all of the distant galaxies are moving away from each other. That is what Larson calls a scalar motion. It's a motion that has a magnitude but has no direction. You can use a balloon and a magic marker to depict that with putting some dots on the balloon. If you blow up the balloon, all of the dots are moving away from each other. That is an outward scalar motion with no particular direction, or all directions outward. If you suck in the balloon, then that is an inward scalar motion. All of the dots are moving toward each other. Okay, now also time and space have only come in discrete units. There is no 0.36 units of space or time. There's only one, and then there's two, and then there's three. They come in chunks. Those chunks are very small, so it looks continuous, but it isn't. And 1 unit of space in 1 unit of time is the speed of light. So the speed of light is 1. And that 1 is the speed from which Larson makes his measurements from. He calls that the progression of the natural reference system. So unlike the normal scientists who make their measurements from 0, when you say the car is moving 10 miles an hour, or 20 miles an hour, that means that it is moving from 0. But in Larson's system, he measures that as far as a displacement from the speed of light outward. So in Larson's system, half of the universe is moving slower than the speed of light. That is the half that we're familiar with, that Einstein was familiar with when he said that the speed of light is the maximum speed of the universe. But for Larson, that's only half of the universe. The other half is the half that is moving faster than the speed of light, where the speed of light is the minimum speed of the universe. And Larson calls that the cosmic sector. And that has to do more with life phenomena, with intelligence, and other things, maybe of a different nature from all of those. So that's kind of where Larson's system, kind of how it works. Now we are looking at his 1979 book here that is called Nothing But Motion. And this book, we're in chapter 8, which is called Motion in Time. Now, motion in time is really motion faster than the speed of light. If the motion is in space, that means it's slower than the speed of light. And if it's in time, it is faster than the speed of light. We're getting ahead of ourselves a little, but this can be described with an astronomical example, such as a white dwarf star or an exploding a supernova. So if you have a star that explodes, it explodes in space, so it's going outward at a fast rate. But if that explosion is actually so powerful that it propels its its matter faster than the speed of light, then the motion is actually in time. It explodes in time, not in space. And since time and space have a reciprocal relationship, we don't see time, we only see space. So we see an explosion in time as an implosion in space. And so if the star blows up at faster than the speed of light, then it actually implodes and gets smaller, according to the way that we perceive it. It's actually exploding in time, but we see it as an implosion in space by the reciprocal postulate. So that is how Larson explains white dwarf stars in particular. And if it's a galaxy, then he calls it a quasar. Quasars and pulsars and white dwarf stars are all explosions at faster than the speed of light. Okay, now we're going to get into his discussion of these matters, motion in time here. I think he's going to leave the astronomical stuff a little bit behind and go into some other stuff. But let's hear how he starts here. The way in which motion in time manifests itself to observation depends on the nature of the phenomenon in which it is observed. Large redshifts are confined to high-speed astronomical objects, and a detailed examination of the effect of motion in time on the Doppler shift will be deferred to our volume on astronomy, where it will be relevant to the explanation of the quasars. At this time, we will take a look at another of the observable effects of motion in time that is not currently recognized as such by the scientific community: its effects in distorting the scale of the spatial reference system. It was emphasized in Chapter 3 that the conventional spatial reference systems are not capable of representing more than one variable, space, and that because there are two basic variables, space and time, in the physical universe, we are able to use the spatial reference systems only on the basis of an assumption that the rate of change of time remains constant. We further saw earlier in this present chapter that all speeds of unity or less time does, all speeds of unity or less, I think this is a typo, does in fact progress at a constant rate. And all variability is in space. It follows that if the correct values of the total time are used in all applications, the conventional spatial coordinate systems are capable of accurately representing all motions at speeds of 1 over n. That is less than the speed of light, because 1 is the speed of light, and n is 1 or more. But the scale of the spatial coordinate system is related to the rate of change of time. And the accuracy of the coordinate representation depends on the absence of any change in time other than the continuing progression at the normal rate of registration on the clock. At speeds in excess of unity, space is the entity that progresses at the fixed normal rate, and time is variable. Consequently, the excess speed above unity distorts the spatial coordinate system. In a spatial reference system, the coordinate difference between 2 points A and B represents the space traversed by any object moving from A to B at the reference speed. If that reference speed is changed, the distance corresponding to the coordinate difference AB is changed accordingly. This is true irrespective of the nature of the process utilized for measurement of the distance. It might be assumed, for instance, that by using something similar to a yardstick, which compares space directly with space, the measurement of the coordinate distance would be independent of the reference system. But this is not correct. As the length of the yardstick, the distance between its two ends, is related to the reference speed in the same manner as the distance between any other 2 points. If the coordinate difference between A and B is x, when the reference speed has the normal unit value, then it becomes 2x if the reference speed is doubled. Thus, if we want to represent motions at twice the speed of light in one of the standard spatial coordinate systems that assume time to be progressing normally, all distances involved in these motions must be reduced by 1/2. Any other speed greater than unity requires a corresponding modification of the distance scale. The existence of motion at greater than unit speeds has no direct relevance to the familiar phenomena of everyday life, but it is important in all of the less accessible areas, those that we have called the far out regions. Most of the consequences that apply in the realm of the very large the astronomical domain, have no significance in relation to the subjects being discussed at this early stage of the theoretical development. But the general nature of the effects produced by greater than unit speeds is most clearly illustrated by those astronomical phenomena in which such speeds can be observed on a major scale. A brief examination of a typical high-speed astronomical object will therefore help to clarify the factors involved in the high-speed situation. In the preceding pages, we deduced from theoretical premises that speeds in excess of the speed of light can be produced by processes that involve large concentrations of energy, such as explosions. Further theoretical development will show that both stars and galaxies do, in fact, undergo explosions at certain specific stages of their existence. The explosion of a star is energetic enough to accelerate some portions of the stellar mass to speeds above unity, while other portions acquire speeds below this level. The low-speed material is thrown off into space in the form of an expanding cloud of debris, in which the particles of matter retain their normal dimensions but are separated by an increasing amount of empty space. The high-speed material is similarly ejected in the form of an expanding cloud, but because of the distortion of the scale of the reference system by the greater than unit speeds, the distances between the particles decrease rather than increase. To emphasize the analogy with the cloud of material expanding into space, we may say that the particles expanding into time are separated by an increasing amount of empty time. The expansion in each case takes place from the situation that existed at the time of the explosion, not from some arbitrary zero datum. The star was originally stationary or moving at low speed in the conventional spatial reference system, as was stationary in the time of the moving system of reference defined by a clock. As a result of the explosion, the matter ejected at low speeds moves outward in space and remains in the original condition in time. The matter ejected at high speeds, speeds greater than light, moves outward in time and remains in its original condition in space. Since we see only the spatial result of all motions, we see the low-speed material in its true form as an expanding cloud, whereas we see the high-speed material as an object remaining stationary in the original spatial location. Because of the empty space that is introduced between the particles of the outward moving explosion product, the diameter of the expanding cloud is considerably larger than that of the original star. The empty time introduced between the particles of the inward moving explosion product conforms to the general reciprocal relation and inverts this result. The observed aggregate, a white dwarf star, is also an expanding object, but its expansion into time is equivalent to a contraction in space, and we see it in its spatial aspect. Its diameter is substantially less than that of the original star. It thus appears to observation as an object of very high density. The white dwarf is one member of a class of extremely compact astronomical objects discovered in recent years that is today challenging the basic principles of conventional physics. Some of these objects, such as the quasars, are still without any plausible explanation. Others, including the white dwarfs, have been tied into current physical theory by means of ad hoc assumptions. But since the assumptions made to explain each of these objects are not applicable to the others, the astronomers are supplied with a whole assortment of theories to explain the same phenomena, extremely high densities. It is therefore significant that the explanation of the high density of the white dwarf stars derived from the postulates of the reciprocal system of theory is applicable to all of the other compact objects. As will be shown in the detailed discussion, all of these extremely compact astronomical objects are explosion products, and their high density is, in all cases, due to the same cause: motions at speeds in excess to that of light. This is only a very brief account of the complex phenomenon that will be explained in full detail later, but it is a striking illustration of how the inverse phenomena predicted by the reciprocal relation can always be found somewhere in the universe, even if they involve such seemingly bizarre concepts as empty time or high-speed motions of objects stationary in space. Okay, just wanted to point out, because Larson didn't do it right there, that Larson himself predicted the existence of quasars before they were discovered. Okay, quasars were discovered in the early 1960s. In Larson's first volume of this first edition of this 3-volume work, this Nothing But Motion is the first book in a 3-volume series called The Structure of the Physical Universe. And this is the second edition. But in the first edition that came out in the late 50s, he predicted the existence of quasars. So the theory works as far as that goes. Okay, have a great day. We'll see you tomorrow. Thanks for tuning in.